Welcome to the Phenomenological Alliance channel. In this video, we will highlight the problem of excluding the human perspective in the study of nature.
In 1687, Sir Isaac Newton published the book Principia, stating the concept of universal gravitation.
Any two bodies are attracted by a force proportional to their mass and inversely proportional to their separation squared.
Upon publication, the concept of the existence of an attractive force between matter was heavily criticized. Newton's hypothesis ignited a great controversy within the realm of cosmology. Before Newton, the motion of Earth was explained by the vortex theory. The Sun was not perceived as a material object, rather, it was seen as the polar opposition to terrestrial forces. In Newton's model, the planets move by inertia, and their rectilinear paths are bent by gravitational force. In the vortex theory, the Sun as a concentrated etheric nucleus creates the cosmic vortex of ether, and the planet's centrifugal force acts as a balancing force to the vortex suction power. Newton's hypothesis also caused debates about the nature of mechanical force. Before Newton, it was believed that a mechanical force is a contact quantity, and that between material bodies there is no action at a distance. A mechanical force must have a tangible physical cause, as is the case when a magnet attracts iron. Newton did not delve into the physical nature of gravity, stating,
"I have not yet been able to discover the cause of these properties of gravity from phenomena, and I feign no hypotheses."
Newton's theory was widely accepted following the Cavendish experiment, which is famed for empirically demonstrating the attractive force between material objects. The question of the physical nature of gravity gave rise to many hypotheses, and the modern understanding of the nature of gravity is the one put forth by Albert Einstein. Gravitational lensing is a concept developed by Einstein in the early 20th century. In his paper on the influence of gravity on the propagation of light, after assuming that the cause of gravity should be sought in the curvature of space and time, Einstein predicted that extremely massive celestial bodies, such as galaxy clusters, cause significant curvature in space-time. The theory of gravitational lensing gained acceptance when it was spotted that light of peripheral stars, hidden by the Sun during a solar eclipse, is bent. The bending of the light trajectory caused by the Sun's mass enables the observation of objects that are not directly in the path of the light's rectilinear propagation. The embrace of such concepts fundamentally altered our understanding of the world. In cosmology, gravitational lenses serve as tangible evidence affirming the Sun's immense mass. Moreover, the acceptance of space-time curvature had profound consequences for understanding the fundamental principles of nature. Among the most significant outcomes are length contraction and time dilation. Essentially, this implies that an object in motion appears shorter in the direction of its motion, or that it is possible to travel into the future by reaching the appropriate speed.
Let's explore the real meaning of the concept of the bending of a light ray from a human perspective. Looking at Einstein's original sketch of the model of gravitational lensing, we must notice that modern physicists depict the phenomena in nature as if man doesn't exist. In reality, we observe the images of distant stars obscured by opaque objects. During a solar eclipse, the Sun is obscured by the Moon. The picture seen on the edge of the object is increasingly deformed. The picture seen through small openings or around the perimeter of the screen is magnified. When this fact is represented geometrically, it looks like the projection of the image points on our retina is no longer rectilinear. The actual phenomenon is the magnification of the image, not the bending of the light trajectory. The phenomenon can be studied through a small opening created by the fingers of the hands, where we can notice the magnification of the text. When people have difficulties seeing clearly, they squint their eyes to magnify the image they are looking at. Believing that mass, that is, gravity, can bend the trajectory of light is akin to believing that an image viewed through our fingers is deformed due to the mass of the fingers. The size of image magnification depends only on the size of the opening. The smaller the opening, the larger the magnification of the image. The conviction that objects shrink when they accelerate was born from a misunderstanding that the image of the objects we observe changes due to the change of the viewing perspective. However, it's a matter of our perception of the object size rather than an actual alteration of the object size. On the other hand, the idea that people can travel into the future belongs to the realm of fiction, not reality.
The famous German physicist and the founder of quantum physics Max Planck once stated,
"The true goal of scientific endeavor was to establish the nature of the external world independent of the human observer."
This attitude stands in complete contrast to the phenomenological approach. For phenomenology, the ultimate source of all meaning and value is the lived experience of human beings. Phenomenology proceeds from the insight that man cannot be understood through nature, but quite on the contrary, nature can be understood through the understanding of man. Therefore, phenomenology as a method places the understanding of observation and the understanding of human consciousness about the observed as the prerequisite for cognition.